All right, let's talk about something that's literally holding our entire universe together. It's this invisible force that keeps our feet planted firmly on the ground, but at the same time, it's orchestrating this grand cosmic dance of planets, stars, and even entire galaxies. We're talking about gravity, of course. But here's a weird thought for you. Newton's famous law of gravity says that every single object with mass pulls on every other object. So why aren't you being gently tugged toward your desk right now? Or your chair? Or for that matter, why isn't that coffee cup over there pulling you in? It's a great question, and the answer is actually really elegant. You see, the first huge leap from Newton was realizing gravity isn't just for planets and stars, it is universal. I mean, right now, you are gravitationally pulling on the screen you're watching, and it's pulling right back. All around you, there's this invisible, silent tug-of-war happening between everything. Now, Newton's law gives us the official rulebook for that cosmic tug-of-war. Okay, that sounds a little dense, but it really just boils down to two key things: how much stuff or mass the objects have, and of course, how far apart they are from each other. And this slide just nails those two rules perfectly. First, the more mass something has, the stronger its gravitational pull. Simple enough. But second, the farther away you get, the weaker that pull becomes. And it weakens fast. Think of it like a can of spray paint. The farther you are from a wall, the more the paint spreads out, and the thinner the coat gets in any one spot. Gravity works just like that. And here is the whole shebang, wrapped up in one famous formula. F is the force, the m's are the masses of the two objects, and d is the distance. But what about that big G? Well, that G, my friends, is the secret ingredient. It's the key to solving our entire coffee cup mystery. So how does this finally solve our puzzle? Why don't we feel the pull from all these everyday objects? The whole secret, the entire reason, is hidden inside that mysterious capital G, the universal gravitational constant. And there it is. Just look at all those zeros. The value of G is, well, it's heroically tiny. It's this fundamental number that's the same everywhere in the universe, and it basically sets the volume knob for gravity. And because this number is so incredibly small, it means you need a truly colossal amount of mass in the equation just to produce a force you can actually notice. This chart just says it all, doesn't it? The gravitational force between two people standing near each other is, well, it's basically zero, a tiny, almost invisible sliver. But what happens when one of those objects is the entire planet Earth? Boom! The force becomes huge. It becomes the force that we feel every single second, the force we call our weight. So here it is, the aha moment. Your coffee cup is pulling on you, but because its mass is so small and that constant G is so tiny, the force is completely, utterly unnoticeable. Gravity is basically a background singer until a planet or a star steps up to the mic to take center stage. Okay, so we've cracked the coffee cup mystery. Now let's zoom way out. How does this same weak but always-on pull manage to keep the moon locked in orbit around us and our Earth looping around the sun? The answer is this beautiful, perfect balance between motion and gravity. It works just like this. The moon is moving really fast, and its natural tendency, its inertia, is to just fly off in a perfectly straight line deep into space. But at every single moment, the Earth's gravity is pulling it sideways. It's not a strong enough pull to make it crash into us, thank goodness, but it's just right to constantly bend its straight path into a circle. So an orbit is really just a state of continuous falling and always missing the ground. To really wrap your head around this, let's try a quick thought experiment. What if we had a cosmic remote control and could just switch off Earth's gravity for a second? What would happen to the moon? It would instantly stop falling. It would just continue on the straight path it wanted to take all along, flying off in a straight line, like a rock being let go from a slingshot. This really shows that gravity is the only thing holding that leash, constantly providing that inward tug that creates the orbit. And this brings us to something that trips up a lot of people, a common point of confusion that gravity helps us clear up completely. We tend to use the words mass and weight as if they're the same thing, but in physics, they are completely different. So what is the difference? It's actually pretty simple. Your mass is the amount of stuff you're made of, all your atoms and molecules, and that is constant, no matter where you go in the universe. Your weight, on the other hand, is just the measurement of the force of gravity pulling on that stuff. Go to a different planet, and that pull, your weight, is going to change. Let's look at this example. A 70-kilogram person has a mass of 70 kilograms, right here on Earth. And if we could magically transport them to the moon, their mass would still be 70 kilograms. The amount of them hasn't changed. But their weight? Oh yeah, that would change big time. On the moon, where gravity is only about 1/6 as strong, they'd weigh dramatically less. They'd feel incredibly light. So when you step back, this one simple law explains so much about our universe. It's the reason we have weight and don't just float away. It's the architect of our entire solar system, keeping the planets in their lanes. It even reaches across the vastness of space to cause ocean tides and to hold the billions of stars in our galaxy together. And that leaves us with one last, kind of mind-bending thought. Of the four fundamental forces in nature, gravity is by far the weakest. It's not even close. And yet, this cosmic weakling, with enough mass and enough time, has managed to build the entire cosmos we see today. It really makes you wonder, what incredible secrets are the other, much stronger forces still waiting to reveal?